7.4 is evaluate logarithms and graph logarithmic functions. So a logarithm is like the inverse or the opposite of an exponent. So if we have b to the x power equals y, as a log, this would be log base b of y equals x. So this kind of helps us when we don't know the exponent. On your calculator, you do have two buttons. One of them says log, and this means with a log of base 10. And this is the common log. So just like with square roots, how we don't write the 2 on the outside, if you just see a log, that means the base is a 10. And the other button you probably have on your calculator is ln. So this is log with the base of e, and this is the natural log. Okay, so in this first section, we want to evaluate the logarithm without a calculator. Number 1 says log base 6 of 216. So there's two different ways you can think about this. You can think 6 to what power equals 216. Or what you can do is rewrite 216 with a base of 6. So log base 6 of 6 to the third, and both of these will equal 3. So the answer for this is the exponent, and since we know 216 is 6 to the third, 3 would be the answer. For number 2, we have log base 16 to the 1/4. So again, we can think of this as 16 to what power equals 1/4, or we can rewrite 1/4 with a base of 16. So that would be log base 16, and 1/4 would be 16 to the negative 1/2 power. So it's the negative 1/2 power because 16 to the 1/2 would be 4, since that's the square root of 16, and it's negative because it's 1/4. So in both cases, the answer would be negative 1/2. Next one, we have log base 5 of 625. So again, it means 5 to what power is 625? Or we can rewrite 625 as 5 to the 4th. So again, the exponent's going to be the answer, and both cases the answer is 4. Okay, next we want to simplify the expression. If the bases are the same, then we can cancel them out. So if the base for the log and the base for the exponent is the same thing, we can cancel it. So that means I want to rewrite 36 with a base of 6. And 36 is 6 to the second power. So since this base and this base are now the same, it cancels out. So all we're left with is the exponent, which is going to be 2x. For number 5, we have 10 to the log 8. And if you remember, since there's no base for the log right here, that means there's an imaginary 10 right here. And again, since they have the same base, both of the bases are 10, this will cancel out, so this equals 8. Next, we have number 6, log base 2 of 32 to the x power. So we want these two bases to be the same. So I can rewrite 32 as 2 to the 5th power, and then we have the x on the outside. And since these two match, this will cancel out, so this will become 5x. Okay, number 7, find the inverse. So in order to find the inverse, we're going to switch the x and y's. So x will equal 7 to the y power. And we don't want y in the exponent, we kind of want to get rid of that 7. So to get rid of it, we're going to log 7 both sides. So if I write this out, this would be log 7x equals log 7 of 7y. So now this log 7 of 7 part will cancel out. So we get log 7 of x equals y. For number 8, we have y equals 6 plus log x. So first we're going to switch x and y. And then we want to solve for y, so we have to subtract 6 first. So we get x minus 6 equals log y. And the base of this log is 10, so we want to use 10 as a base so that this part will now cancel out. So now our line in blue is like the exponents, so this would be 10 to the x minus 6 power equals y. Okay, next we're going to graph and state the domain, range, and vertical asymptote. So for number 9, we have y equals log base 2 of x. So I'm going to make a table. And I'm also going to list out some numbers. So I know 2 to the 0 power will equal 1, 2 to the first power equals 2, and 2 to the second power equals 4. And I'm going to use that to help me list some points. So these answers on the right, these would be the numbers that we plug in for x. So that means that would be 1, 2, and 4. And the exponents would be the y value. So that would be 0, 1, and 2. Okay, next we want to find the domain, range, and vertical asymptote. Domain means the possible values of x, and this time since x is the answer of the, like when we have an exponent, no matter what we plug in, x can never equal 0 or be negative. So 2 to no power will give you a 0 or a negative number. So for the domain, this would be x is greater than 0. Sorry, let me move this back. So that means the vertical asymptote is going to be at x equals 0. And these two numbers will always be at the same place. So it's right here. And we can use that line to kind of help us find the shape of the graph. So we have the point 1, 0, 2, 1, and 4, 2. So the graph will look something like this. And just like the horizontal asymptote, our graph won't touch or cross the vertical asymptote. For the range, this is possible values of y, and if we look at the graph, it's going to go down forever and up forever. So range is going to be all real numbers. And range will always be all real numbers for all of log problems. Okay, number 10. So again, we want to find a couple points. I usually like doing 3 points. And this time our base is 1/3. So we have 1/3 to the 0 power. I know that's going to equal 1 because anything to the first or 0 power is 1. And I'm also going to do 1/3 to the negative 1 power. I'm not choosing the first power because that would be a fraction. I mean, I guess you could plug that in. But anyways, I'm just going to choose negative 1 because 1/3 to the negative 1 power is 3. And you can choose another one. So I'll just choose 1. That'll equal 1/3. Okay, so the x values are going to be the answers, which was 1, 3, and 1/3. And then the y values are going to be the exponent. So 0, negative 1, and 1. And for this problem, we have the same thing as the first one. So domain's going to be x is greater than 0 because there's no plus or minuses in the problem. And we have our 3 points. We have 1, 0, 3, -1, and 1/3, 1. So our graph is going to look something like this. The vertical asymptote's at x equals 0, and range is going to be all real numbers. Okay, number 11. We have y equals log base 5 of x minus 4 and then plus 2. So first, I want to pick numbers that I can plug into here. So the first number that I would want this equal to is 5 to the 0 power, which is 1. And then the next one, I'll pick 5 to the first power. So I'm using a base of 5 because that's the base here. And I want this to be the answer of the exponent. So 5 to the first would be 5. And then we can do 5 to the second power, which would be 25. So now we're going to solve for x in all of the equations. And we get x equals 5, 9, and 29. So these are the numbers that are going in the table. Okay, when we plug in 5 for x, that means this part in the blue box is going to equal the exponent, because that's like the definition of log. So when x equals 5, the exponent was 0. So that means everything in that blue box is going to equal 0. And our equation is y equals the blue box plus 2. So that's why that's going to be 0 plus 2, which is 2. Next, when x is 9, that's this middle one. The exponent was 1. So this will be 1 plus 2, which is 3. And when x is 29, the blue box is going to equal 2 because that's the exponent. So this would be 2 plus 2, which is 4. This time for the domain, it's going to be a little different because we have x minus 4 instead of just x. So what we want to do is set this greater than 0. So whatever we have inside the parentheses here, we're going to set greater than 0. Because this number can never equal 0 or be negative. Then we're going to solve, so add 4, and we get x is greater than 0. So, x is greater than 4. So that also means the vertical asymptote is going to be at x equals 4. So our vertical asymptote is here, and then we can plot our 3 points. So we have the point 5, 2, 9, 3, and 29, 4, which is somewhere off the graph. And they'll look something like this. Now for the range, this will always be all real numbers. Okay, last problem. We have y equals log base 1/2 of x plus 2 minus 1. So first we want to look at this here, which is x plus 2. And we want to set this equal to the answer for the exponent. So we have 1/2. I like doing 0 as an exponent because it's really easy. It's always going to be 1 for every problem. Okay, next let's do 1/2, and I would pick a negative exponent so that we have whole numbers, but you can choose a positive one if you want to deal with fractions. I just personally don't like fractions that much. Okay, so 1/2 to the -1 power is 2, and for the last one we have 1/2, and I'm going to choose to the -2 power, and that's going to equal 4. So now we're going to solve all of these, and we get x equals -1, 0, and 2. So those are going to be my x values on the table. When x is -1, the exponent was 0, so this entire log part is going to equal 0. So that means we have 0 minus 1, which is -1. When x is 0, the exponent is -1, so that's going to be -1 minus 1, which is -2. And when x is 2, that means the exponent is going to equal -2. So -2 minus 1 equals -3. Okay, for the domain, we have x plus 2 in the parentheses, and we want to set this greater than 0. So we're going to subtract 2 on both sides, and we get x is greater than -2. So our vertical asymptote is going to be at x equals -2. And range is always all real numbers. Okay, so for the graph, we have a vertical asymptote at -2. We have the point -1, -1, 0, -2, and 2, -3. And I can use that and the vertical asymptote to draw my graph. And it'll look something like this.